Hello, and welcome to our first online lecture format. We're going to begin where we left off before the semester, went the way it did. I started this section in one of my two classes, but I'm going to start from the beginning once again. It has been a long couple weeks. So we're going to be talking about more on division of radical expressions. Specifically, what that means for us is rationalizing denominators. Okay, so the examples that I do are going to be from the handout that's on Blackboard. I'm going to try to continue that pattern. So ideally, what you should do is print out, or otherwise follow along closely to the handouts and take notes, lecture notes, just as if you were in, an ordinary class, okay, classroom setting. So today, and this might be a rough video. Again, it's my first foray into this, so just bear with me, and hopefully this becomes seamless as time goes on. So we're going to be talking about rationalizing denominators. So what does it mean to rationalize a denominator? Well, for instance, you may not believe me when I tell you that these two fractions are actually the same. Okay. They have different numerators and denominators, but as numbers, they are equal to one another. You could try on a calculator and do the division yourself, and you will see that indeed these do come out to the same number. The one on the left here, okay, again, these are the same number. Okay, this version of the number, okay, has an unrationalized denominator. Okay, the one on the right-hand side has a rationalized denominator. The major difference being, we're focusing on the denominator here. The one on the left has a radical expression. The one on the right does not have a radical expression in the denominator. So the process of rationalizing the denominator means to rewrite the fraction such that it does not have any radical expressions lingering down there, okay? So there's a process by which we can remove the radical in the denominator by multiplying it by some clever expression, and by carrying out that multiplication and simplifying, we will remove that unrationalized part of the denominator, okay? So a unrationalized denominator, so a denominator is not rationalized if it contains a radical expression. Technically, one that cannot be removed by simple simplification. Meaning that you can't just take the square root or just take the cube root and it disappears. Okay, so the process by which we take an expression that does not have a rationalized denominator and we produce one that does have a rationalized denominator, this is called rationalizing the denominator. When you look at answers in the back of your textbooks or online, often they will not, sometimes they will, but often they will not leave answers, okay, with unrationalized denominators. And this is going to be especially important when you move on to your next math course, like calculus or college algebra, whatever it may be, often the expressions will not contain these square roots in the bottom. Okay, rather they'll have a simplified version of that. So how do we do it? What's the process? How do we actually rationalize a denominator? Well, we're going to multiply by something. So 2 rationalize a denominator. Multiply by, and this is important, to keep a number the same, if you're multiplying it by something, the only number you can multiply that doesn't change what you started with, the only number you can multiply by is 1. Okay, so we're actually going to multiply by 1, but not just 1, because 1 wouldn't change the look of the expression, but there's different versions of 1 we can multiply by. So we're going to multiply by 1, but in a clever way. Okay. So what do I mean by that? Notice that 1 is the same thing as 3 over 3, which is the same thing as square root of 7 over square root of 7. That's also equal to the cube root of 2x over the cube root of 2x. These are all equal to 1. They're just different looking versions of that number 1. And which one we're going to multiply by depends on what we're starting with. Okay. What we want to do is multiply by 1 such that the denominator, after simplification, completely simplifies having no radical. Having no radical expression. Before I get to all the examples on the handout, I just want to show you kind of the process. So up here, I'm going to show you that these two numbers are actually the same. So you want to show that 1 over the square root of 2 is actually the same as the square root of 2 divided by 2. Okay. So to do that, I'm going to multiply this by 1. And that's going to be our clever 1, such that the end result, this denominator, okay, has, after simplification, such that this denominator no longer contains a radical. All right. So what do I multiply by? Well, in this case, if I multiply by the square root of 2 divided by the square root of 2, just multiplying across the top, I'll have 1 times the square root of 2. That's equal to the square root of 2. And in the bottom, I'll have the square root of 2 times the square root of 2, which is the square root of 2 times 2. Okay, that's the square root of 4. So what we just ended up with in here, in the denominator, this is the square root of a perfect square. That's what we want, because if I take the square root of a perfect square, the square root goes away. Right? So square root of 2 over 2. So these two are identical numbers. All we did was multiply this one by 1, but we changed how it looked. Okay, we changed how the fraction looked. So that's kind of the whole point. Let me just do one more example, something with a cube root maybe. let's say I wanted to rationalize this denominator. Okay, 2 divided by the cube root of 9. Now, it's not going to be quite as simple as what we just did. We have to think a little bit more, right? So I have to multiply this by a fancy version of the number 1 in order to get, so, and the theme is going to be, if you have a square root, you're going to end up multiplying by some other square root. If you have a cube root, you're going to be multiplying by some other cube root. So I eventually want this to end up being the cube root of some cube root of some perfect cube. Meaning that I can fully simplify that new denominator, right? So here's the thought process. And again, we're going to see several examples in a little bit on the handout. But I have to think, okay, so I'm multiplying this 2 over the cube root of 9, right? So I'm multiplying this 2 over the cube root of 9 by something, okay, that will give me a perfect cube in the bottom. So our focus is on the denominator once again. So I have to think, all right, what can I multiply the cube root of 9 by? The cube root of what? What can I multiply the cube root of 9 by that will give me the cube root of a perfect cube? So this is where it comes in handy to remember that list of perfect cubes, right? So remember our perfect cubes, right? When we cube 1, we get 1. That's nothing special. When we cube 2, we get 8. When we cube 3, we get 27. When we cube 4, we get 64, and so on. Right? So we went over similar lists in the past. So what I think is the fastest way to figure out what we multiply by is, okay, I have to figure out what I multiply by 9 that gives me a perfect cube. So I'm going to look through this list and think, what here is divisible by 9? Right? And the smallest thing is usually going to be the best. You don't want to, there's going to be many numbers you could actually choose potentially that will help you simplify this, but the smaller number is going to be the best. So what's the smallest number that I can multiply by 9 that gives a perfect cube? Well, the smallest perfect cube in this list is 27 that is divisible by 9, right? So I can get a 27 here if I multiply the cube root of 9 by something that gives me the cube root of 27. And with a little bit of thought, you'll realize that should be a 3. And to make sure we're multiplying by 1, whatever you write in the bottom here, you also have to write up top. Again, the whole point was to get the end result, the cube root of a perfect cube. Just like before, we wanted the square root of a perfect square, and that theme will continue. We'll want the fourth root of a perfect fourth power, and so on and so on. Right? So what happens is, when I multiply the numerators together, I'll get 2 times the cube root of 3. Well, I can't really simplify that, right? So they're unlike terms. We're just going to, this isn't even a radical term. So 2 times the cube root of 3, there's no way to really put that together. So we just leave it that way. So what we're doing in many cases is sacrificing the prettiness of the numerator, right, the neatness of the numerator, to have a nicer denominator. Now we're not done yet, okay, so the whole point is to get rid of that radical expression. So I'm just going to simplify that denominator, and I'll get 2 times the cube root of 3 divided by 3. Right, so 2 divided by the cube root of 9, what we had over here, is the exact same number as 2 times the cube root of 3 divided by 3. The only difference is we got rid of the radical in the denominator. And again, this is how most answers in most math books are going to be stated. Even though both are technically the same number, this one is preferred on the right here. We prefer this one. Okay, so that's the process. Now I'm gonna stop this video. Just cover the basics here. Now we're going to look at the handout examples, and you'll see many more examples.